Good morning, and thank you for being here. First, a few words about myself. My name is Xinfeng Liang. I'm an assistant professor in physical oceanography. Actually, I just started this position early this year, so I'm also relatively new to this college. Today, I'm going to talk about the ocean's role in the climate system. It's a fairly complex system. Here, I will only focus on the physical oceanography part and present like two cases, basically what I have been doing in my group. Let's start with it. Oops, it didn't work. This is expected. So
just move your mouse off screen.
Okay, great, that's good. Let's start with this kind of a big question. How does the ocean affect the climate system? We know that the ocean is a major element of the climate system. It covers more than 70% of the Earth's surface. It has a huge amount of water inside. So physically, it's very important for the storage of heat, as well as the transport of heat among different latitude and between different depths. The reason we have this relatively pleasant climate today is because the ocean can transfer a huge amount of heat from the tropical region to the high latitude region. Chemically, the ocean is also very important because the ocean is a major storage of carbon. And so it's very important for the carbon cycle, and we all know that the carbon dioxide is a very, very important greenhouse gases and plays quite an important role in the change of climate. The seawater carbonate system also very important for the marine carbon cycle as well as the global carbon cycle, and therefore important for the climate change. We have experts in this college who know much better than I do about these topics. And biologically, the photosynthesis and the respiration processes in the ocean can significantly affect the carbon dioxide in the ocean. So itself will be very important for the carbon cycle and the climate. Even geologically, the ocean is very important. I noticed recently there are very few very interesting studies showing a good correlation between the mid-ocean mid-ocean region eruptions and the 100K year of climate change. So you can see from here you can see the ocean really can affect the climate system in a number of different ways, and actually all those different ways are all coupled together. That means here the College of Marine Science is a great place to explore this very big, very important question, because we have experts on all these different disciplines. So what my group is doing, the major research interest of my group is basically these two things. First is the role of ocean in the climate system. Particularly, I'm interested in how the physical processes affect the climate, meaning the ocean circulation, how the ocean circulation and the mesoscale eddies and other processes affect the redistribution of heat, salt, and water inside the ocean. And the other is purely ocean dynamics. I'm particularly interested in the mesoscale eddies and the internal waves and ocean mixing, and how those different physical processes couple together. And later in this talk, I will show you a case how those different processes couple together. And the tools I'm using are mainly these three different things. The first is observations. By analyzing the satellite and the in-situ measurement, satellite data, I mean use the sea surface height anomaly. For the in-situ measurement, I'm going to use the deep ocean current meter measurement, and as well as some temperature salinity profiles. So eventually, you guys will have a first-hand experience with this very conventional classical measurement in the ocean. I also use numerical models to study ocean processes. Particularly, I use this MIT GCM, which is a primitive equation general circulation model. You can use it to learn very fancy stuff. You can also use it to focus on particular processes. So I mainly use this to focus on particular processes like the energy redistribution of tidal energy redistribution over topography. And another major tool I'm using now is the ocean state estimate, particularly a product called ECHO. Here, ECHO stands for Estimating Circulation and Climate of the Ocean. The ocean state estimate is basically a combination of those two different things. The reason we developed this ocean state estimate because the observations we have at present usually have gaps, spatially and temporally, because the in situ measurement inside the ocean is really difficult to get and very expensive to get. So to study global problems, you need to have like global coverage, but that means you have to fill in those gaps where you don't have data. There are many ways to do this. Some people use a very fancy statistical model to fill in those gaps, and there are also people use very simple assumption. You just make some assumption about those gaps, then fill in those gaps. And there's another way fill in those gaps is combine the information we have from the observation as the ocean dynamics we have known. And here the numerical model kind of represents what we know about the ocean dynamics. Then you use and combine these two stuff, you get a global 3D time-involving data set. And this data set usually includes the temperature, salinity, velocity, and another diagnostics. So with this estimate, you can do a lot of things about the global scale processes. So here I go to the first case. It's about the vertical redistribution of ocean heat. As I mentioned, in the textbook, you will see that there have been a lot of studies talk about the meridional heat transport, basically how the heat would transport from the tropical region to the high latitude, like that. But in the vertical direction, there are really only, I think, a limited study talking about this. The motivation for this study is mainly from this plot. This plot summarizes a number of studies focusing on the upper ocean heat content change since 1950. You can approximately consider this, equal this to temperature change. You can see that even though there are huge discrepancies among different studies, all those studies show kind of upward trend after 1970. So this is called the upper ocean warming. The conventional idea, and people use this as evidence of global warming. The conventional idea is like people just put too much carbon dioxide into the atmosphere. So due to the greenhouse gas effect, you will break the original balance. So you have more heat stored in the climate system. Then the ocean, as a part of the climate system, will warm up. So people think this is consistent with that idea. But we need to notice that all these results is only the up ocean, only the up. Some people present result about up 700 meters, some people present up 2,000 meters. Those are the region we really have some observation. Below 2,000 meters, we don't have much observation to make any conclusive result. So then we go to this diagram. You see the change of the upper ocean temperature or heat content is actually determined by the air-sea heat flux as well as the heat passing through the lower phase of the upper ocean. So there have been a lot of studies talking about the air-sea heat flux. I mean, even though there are actually a large discrepancies among the different studies, but all those studies show that there's a heat into the ocean during roughly this time period. But what's going on here? We don't actually know. So, I mean, it could be, I mean, in the ocean, you can get a heat down, you can also get a heat up. Because the ocean itself, the very complex dynamics inside the ocean. So I just use the echo estimate to see what's going on at surface and what's going on inside the ocean. This plot shows the temporal mean of the air-sea heat flux at surface. You can see this very, very conventional picture that the ocean receives heat at low latitudes and release heat at high latitudes, even though there are some complex features that are related to the ocean circulation. If you do a mean of this picture, you get a number like 0.3 watts per meter square. That means during this time period, that's from 1992 to 2011, during this time period, you have net heat getting into the ocean. So that means the whole ocean will warm up during this time period. But for a particular layer, like I said, for the upper ocean, whether this the warming of the upper ocean is purely due to this, or is a combination of this and the heat passing in the low phase, need to be checked. So next step, I just show you the result in the deep ocean. You can see this is the heat transport inside the ocean. Below about 1,000 meters, what you get is this. This is a global mean value. You can see this is a positive value, means the heat was transported upward. So that means if we choose arbitrary depths, for instance, if we choose 2,000 depths, 2,000 meters, you can see that the heat passing these depths actually goes into the upper ocean, goes into the ocean above it. So the warming you see in the upper ocean, like here. First of all, you see warming in this time period, and you get heat from the atmosphere, about this number, and you get the heat from the deep ocean to the upper ocean with this number. So what you see here, at least from this product, the warming of the upper ocean is partially due to the heat it received from the atmosphere. It also partially due to the heat from the deep ocean. So this vertical redistribution of heat inside the ocean actually play a quite important role for interpreting the observed warming. So that reminds us we need to be careful about signal here. We shouldn't simply attribute this to global warming or other thing. Then this is some studies I'm doing and I want to pursue in the future. First of all, I want to kind of separate and see the contribution of different dynamical processes to this vertical heat redistribution. So these dynamical processes include ocean circulation, mesoscale eddies, and ocean mixing. And then, because the echo has the estimate of velocity, diffusivity, so we can also examine the change in those different dynamical processes, like how the vertical velocity or upwelling, downwelling changes, how the ocean mixing changes, and also the external forcing mainly at the sea surface, like the wind stress and freshwater flux, how they change over that time period. And combine all those information, we can get a better idea of the response of the ocean interior to the external forcing. So this is the second case. This is mainly a kind of a regional study, but it has kind of a global implication, I think. It's the influence of mesoscale eddies on the deep ocean dynamics. In the introductory textbook, you can always find plots, figures like this, showing the global mean circulation. You see these arrows, like means the ocean water move like rivers inside the ocean. But if you really go to the data, like a snapshot data, like here, this show a snapshot of the sea surface height anomaly. This is what you can see from satellite data. What you see is features with horizontal scale spanning from like 10 kilometers to hundreds of kilometers. Those features are the mesoscale eddies. So in the ocean, what you can see is actually just eddies, eddies, eddies. Here I want to show you a video. Just click this one. Oops. Here. So this animation shows some result from ocean state estimates. you can see in the ocean, you can see those beautiful structures almost everywhere. Some region you have very strong eddies. Some region you have not that strong, but still some weak eddies. You can see that's what you can see in the ocean. See this beautiful eddies. Okay, I'll stop here because of time. You can. Oh. Oh. Where's the arrow?
You found it?
I can't find it. Yeah. The animation just, that's fine. The animation just want to show you that eddies are everywhere inside the ocean. But the problem is what do we know about eddy are mainly based on the satellite measurement, which can only tell you the surface features of mesoscale eddies. And recently also people use the Argo profiles to study mesoscale eddies, which can get down to about 2,000 meters. So below 2,000 meters, we know really little about mesoscale eddies. So what's the deep ocean signal of mesoscale eddies, and what's the impact of the mesoscale eddies on the deep ocean? Circulation, other physical processes like internal waves mixing. We don't have a very good understanding about that. So to address that question, we use some regional study. We conduct some regional study to try to figure out the impact and the signals of mesoscale eddies in the deep ocean. The region we choose is the East Pacific rise. Here you can see this is Mexico. In this region, from some satellite measurement, you can see many mesoscale eddies features. So the good thing is there's a project conducted in this region. Here you can see that's where those stations are located at. So fairly close. It's basically on the path of those mesoscale eddies. So we try to use this measurement to understand that question. For this measurement, this is the East Pacific rise. You can see the very big topography change in this direction. And those dots show the location of the stations. Each location has like 3 deep ocean current meter moorings. So we want to use those deep ocean current meter moorings to check the mesoscale eddies signal. First thing, I just did a very simple spectra for the deep ocean current to see the different components inside the ocean, in the ocean. And you can see this is actually quite a typical frequency spectra in the ocean. I mean, you can usually find those peaks. Those 2 peaks are tides. I mean, this is a semi-diurnal tide, this is diurnal tide, and this red peak here is something called the near inertial oscillation. It's kind of related to the rotation of the Earth. And this part, we call that subinertial, basically very low frequency currents. So we want to see the relationship between this component with the mesoscale eddies, and then we want to examine whether there are some relationship between these components and these different frequency components. Here, this is the low frequency current in the deep ocean. These time series are the low frequency flow from these 3 stations. You can see they are very like to each other. There's a very coherent timely, and the amplitude of those currents are very similar to each other. So basically, along the ridge crest, you have very similar low frequency currents. Sorry. Across the ridge crest, the story is different. You can see there are stations here, and you can see that these 2 stations, these two are very similar to each other because both of them are very close to the ridge crest. But a little bit further from the ridge crest, the patterns are very different. This difference between stations along the ridge crest and across ridge crest tell you the importance of the local topography in determining the currents in the deep ocean. And then we want to see the relationship between this deep ocean low frequency flow and the surface mesoscale eddies. So this plot shows you the surface geostrophic current, which is related to the mesoscale eddies, which is the solid line here. And